Hi, this is Mrs. Bustamante. Today we're going to talk about Charles's Law. And when we're talking about gas laws, we're going to be talking really about three variables. We're going to talk about how volume, temperature, and pressure relate to each other. And then the first couple laws we talk about, we always leave something constant or we don't change it, meaning we're going to keep something the same throughout the experiment or whatever it is that we're looking at. And when we look at Charles's law, we're going to keep the pressure constant. That means the number of collisions that are happening is going to remain the same. And if we have a gas and we keep the pressure constant, we see that the volume or the amount of space that gas takes up is directly proportional to temperature in Kelvin. So what that means is if you have a volume and it's at a certain temperature of a gas, so you have a volume and a temperature of a gas, and then you take that gas and you either increase, say, the temperature, you would have to increase the volume to maintain that relationship. So if temperature goes up, volume goes up, or if volume of that gas goes up, temperature of that gas goes up. And there's something important to think about and to consider when we're talking about Charles's law and all these laws really, is that we need to do our temperature in Kelvin, and we need to use our temperature in Kelvin, not in Celsius, because Kelvin, remember, has this thing called absolute zero, where all particle motion stops. And to figure out what your temperature is in Kelvin, because oftentimes we don't really measure in Kelvin, we take our temperature in Celsius and we add 273. So we'll just have to do a quick conversion in order to understand that. But another way to think about it is temperature is in our denominator, right? And having zero and or negative numbers in our denominator makes figuring out our comparisons a little tricky and not work sometimes, right? So to see this direct relationship, when one goes up, the other one goes up, we have to work in Kelvin, so we only have positive numbers. So what does this mean? What's kind of an example? Well, let's say we have 10 liters of some gas, and it's at a temperature of 2 Kelvin. And remember, when we use Kelvin temperature, we don't say degrees Kelvin, we just say Kelvin. And I take this same gas, and I want to change the temperature to 5 Kelvin. What has to happen to the volume if I'm keeping the amount of collisions the same? I'm not going to change how many collisions I have. Well, this is basically just an algebra problem at this point, right? I'm going to solve for V2. And by the way, we typically label things as 1 and 2. So you'll notice over here on the left of our equation, we have V1 divided by T1. V1 stands for initial volume, whatever you're starting at. T1 stands for temperature at that initial volume condition. And V2 and T2 stand for volume 2 and temperature 2. They're just whatever conditions we're changing it to. So another way to think about V1 and T1 is initial conditions, and V2 and T2 is final conditions. It's just before and after. So now I just return over here to my problem, right? And I want to see what happens to my volume if I increase the temperature. Well, all I have to do at first is think about algebra, right? I'm trying to get V2 by itself. So my first step here is that I am going to simplify on my left-hand side. So I'm going to take 10 divided by 2, and that gives me 5 liters per Kelvin. And remember, I have to leave my units in there. I haven't canceled anything out. Now I'm going to try and get this V2 by itself, and V2 is kind of like X in algebra equation. So I'm going to multiply both sides by 5 Kelvin, and when I do that, I cancel out this Kelvin, and if I do it to one side, I have to follow the golden rule. I must do it to the other side, so I'm going to multiply both sides by Kelvin. And remember, Kelvin divided by Kelvin is 1, so my units of Kelvin are going to cancel out. So now I'm going to have 5 times 5 gives me 25 liters is my volume 2. And we just said that volume and temperature have a direct relationship. So I increase the temperature, so I would expect to increase the volume in this problem. And so my answer makes sense here, which is great. The other thing I'm going to ask you to think about a lot is, how does this relate to kinetic theory? How does kinetic theory explain this relationship that we just saw? So it's great that you can do the algebra and that you can do the math, but I think the understanding of particle movement is even more important. So you're going to look over here, and we have a container. This container has our volume, right? And we're going to increase and decrease the temperature while we keep the pressure the same, and we're going to see what happens to the volume of those particles. Okay, so as this problem is set up, first we're going to add some particles into this container. And then you're going to notice that we're going to keep the pressure the same. So these particles are moving, and they're moving at some given temperature down here. Notice now we're going to add a little heat. We're going to increase the temperature, and we see that the volume of the container is increasing, but the pressure is remaining the same. Likewise, when it got smaller, right, the pressure maintained the same. The particles slowed down because the temperature went slower and the space was slower. So that's a visualization of Charles' law. Now we're going to look at what happens if we change the volume, right? And we are going to add our particles, and then we're going to keep our pressure the same. And we know that as we change our volume, right, our temperature should also change in order to maintain that. So here we are about 300 Kelvin. We're going to increase our volume, increase the space, and we'll notice that the temperature increases, but our pressure remains the same, just as we would expect in that direct relationship. And then we're going to shrink the volume, and the temperature goes down in order to maintain our pressure in this condition still, just as we would think. So we would see a direct relationship. One goes up, the other goes up, one goes down, the other goes down, just as Charles's law explains to us. And I like these because we can even see the particles moving or slowing down to accommodate for those changes.